Okay, so suppose we have a very large file, maybe the more than 10 GB, so I have written in GB scale. Okay, so maybe 10 GB of file stored in a hard disk, and that file may contain huge collection of integers, it may be huge collection of strings, word. Okay, that may be a long list of words or any other uh, string that has some ordering notation. It may be alphabetical ordering, or it may be number systems well ordered ordering principle, ordering of number system. It may be any kind of ordering. If those collection has the ordering, we can sort them, and all these things stored in a hard disk. Okay, in a hard disk. Now we have to sort them. So how to sort? So there is a beautiful algorithm for sorting this type of for this problem. That is, we already know, all of us know, smart sort. Okay. Smart sort is not developed to just become a example of recursion, first example of recursion. It is very simple, quick, optimal, n log n time taken. But what about the file stored in a disk? So far, whatever the sorting algorithm we have learned, all those sorting algorithm, we take some array of elements and then sort them. So it is assumed that the whole array is in the RAM memory. But here the case is not like that. It is not stored in the RAM memory, it is in the hard disk. So which algorithm will work? I have written merge sort because of some purpose. Because this is the algorithm which is exactly developed for computing the disk file, computing sorting inside a disk file. It is not just a very simple sorting algorithm. It is more powerful than we know. Okay, how it's work actually? Now, what is the difference between elements inside the RAM memory and elements inside the disk memory? So, in general, approximately one one unit of access from RAM memory is if it takes t second, okay, t nanosecond, it is in RAM memory, and 1 unit of disk access, it will be t into 10 to the power 6 nanosecond approximately. So this is the difference. If you are accessing element from the RAM, if it take t nanosecond, the same element you are accessing from the hard disk, it will take t into 10 to the power 6 nanosecond. Okay, approximately. This is not exact. This is approximately. In most of the system, the scale is like 10 to the power 6. It may vary. It may be 10 to the power 5 or 10 to the power 7, depending on which system you are using. Okay, but this difference is huge. Now, so when this is the main concern, once you have started accessing the disk element, your CPU complexity is gone. Okay, CPU complexity has no meaning when you are accessing the disk element. So what we will bother about is the IO complexity. What does it mean? IO complexity? How many IO operation is performed to execute the program? How many total IO operation? IO operation means accessing the element from the disk. But there is an advantage. When we access the disk element, we access to block. Okay. Every time we call for some element on the disk. Disk will return a block of element which contains that particular element. Okay. So there is the beauty of this block memory block access. So what how this merge sort is advantage? Let me write the merge sort program first. What we do if we have a gigantic array, it may be in the hard disk, it may be in the RAM, it does not matter. So let's say the array is A, which is very large, very large, no problem. It is in the disk, no problem. And its first index is P, last index is Q. These are two index starting point, and so we have a 10 GB file, and the first element is P, first position, and the last position is Q. This Q may be very large. It does not matter. It is still an integer. Okay. Now, as usual, what is there in merge sort? We have to check for whether P is less than Q. The algorithm will be executed if P is less than Q only. So we will write if P less than Q, then only we will execute. There is no else part, so else we will do nothing. So if P less than Q, what we will do? First we will compute mid equal to P plus Q by 2. I am writing 4 here to indicate that we will take only the integral part, and then we have P to same array. This array is fixed. You can remove it from the syntax. Okay, no problem. P and not Q. We have to write M here. And again, merge sort. A M plus 1 Q. Okay. These are two times we will call. This is recursion. Two times we will call merge sort program, and then we have a merge function. It takes two sorted array and return another sorted array. So this function is beautiful. We need to pass all this index P, M, and Q. Okay. Now how this merge function work? All those other lines will understand. This is the same function. This operation we have to do every time. Now what this merge function do? Merge function take two element as input, two sorted array as input, and return the merge sorted array. Okay. So how this merge function will work? Let's take two sorted array. Okay. There may be string, there may be element, does not matter. For the understanding, I am taking some example. Let's say 1, 3, 5, 7, 8, 9, 10. Okay. And we are taking here 2, 4, 6, 11, 12, 13. Okay. Both these arrays are sorted array, but if we simply club them, that will not be sorted. So that is what merge function do. Merge function take an extra array and it's checked basically. One pointer at this index, one pointer at this index, it will check which one is less. If there is string, it will check the alphabetical ordering of the string. If there is something else and there is some ordering between them, it will simply compare them and write the smaller one depending on the ordering notation in that particular input. Okay, so we have one pointer here also. What it will do, let's say this is name I, this is name J, and this is name K. So to check between which one is less in I or J, whatever the less, that will be written here, and the corresponding index will be shifted. So I will be shifted from this place to this place, and K will be shifted in every step. Okay, so next time we will compare between 2 and 3 and write the smaller one. So in this way this merge function will work. Now how this is linked with that IO complexity and block and hard disk operation? How it is linked? The beauty of this merge function, actually this merge sort call and merge sort call and this p by q, this is only creating index. Okay, only dividing the index, not dividing the array physically. Array is written as it is wherever it is written. It is only computing the indices starting point, ending point, what portion to access from the array. Okay. Now, beauty of this merge sort function is, let's assume that we have some block. This is one block. Okay. In general, block size may be 100 MB in most of the system, or it may be different. That depends on the system. So when we call some number, let's say first number, the IO operation will return one block. So this is our first block. So how many elements I have taken? 1, 2, 3, 4, 5. 5 elements. Let's say the block size is 5 elements. So we will have 1, 2, 3, 4, 5. 5 element here. 1, 2, 3, 4, 5. Up to this. Okay. This is second block. And we have third block. Okay. Since the file is very large, we maybe we cannot load the whole file into the RAM and process it. Okay, that may not be possible. So what we will do? We don't need to load the whole file at all. The merge function is designed in such a way that we don't need to load the whole file at all. What we will load into inside the RAM, only 3 blocks: first block, second block, and third block. So we'll start this merge function, will start working from the between first block and second block. Okay, and it will write in the third block. Now whatever the block will full, let's say third block is full, we have already at the last element. So this block will be written into the hard disk, one IO operation, and the next block will be accessed from the hard disk. Okay, one read operation. That is one more IO operation. Okay. And if this block is full, it will be sent back to hard disk. So we are not writing anything, we are just reading this. Okay. And the next block will be called, so one more IO operation will be. So once this block is removed from the disk, it is not required again. Okay, in this merge function. Okay, in the next round of merge function, it may be required again. So how many merge function is there? That will be the total complexity. So if the array size is n, so if the array size is, there are n element, let's say capital N, is the n by b is the block size. So those many block will be there inside the file. So capital N number of block will be there inside the file. Now those many block access every time we are running the merge function for the element, okay, in every layer. So if we draw the recursion stack, you can understand this thing, okay. So let's say merge sorter is written as ms, and we have the file size. Let's say it is starting from 1, and we have, for the time being, let's assume 100 element. It may be 100 to the power, let's say 100 into 10 to the power some very large number, 10 to the power 5 or 10 to the power 10, that is no problem. So what it will call, it will call this line p less than q condition is satisfied. So mid will be computed. Once mid will be computed, this line of merge function will be called, okay. So it is going to run the ms 150. It will run this. So it will call its sub function again, and that will run. So if we complete this recursion tree in every layer, we can see the access of the whole array. So how many layers are there? There will be log n number of layers. Why? Because we are dividing by 2 halves, every time dividing by 2 halves. So the height of the tree will become log n, and there will be log n number of times we are accessing the whole element. So total complexity will be what? Those many block, those many capital N number of blocks we are accessing log n time. So there are n number of blocks, and we are accessing log n by b time, okay. That will be the complexity. If you compute it, then you will get this complexity of the merge, okay. And that is why merge sort is, how merge sort is designed. It is actually for, and this sorting algorithm is used in MapReduce function, MapReduce algorithm, which is the main algorithm in cloud computing. Inside that, this algorithm is used. Why? Because there involve lot of disk access. So that is the purpose why merge sort is designed, and it work in this way. Okay. And we can merge, other than taking 2 sub-array, we can take 3 or 4 sub-array at a time and merge them, okay. That has some different name. We can call that funnel sort, or some other name also it has. But this is the core element. There are team sort and many sorting algorithm, but the core idea is this, okay. If you are going for insertion sort or quick sort, then the access will not be the in linear sequence, okay. Means it may access this element too, then it want to access, so there will be lot of block swapping, okay. Lot of block swapping, insertion sort, quick sort will fail. Okay, it will access one block, whole block. Then from that block, it will take one element and then do some operation and return the whole block. So that will be the wastage of lot of IO operation, and the IO complexity will be high. Okay, that's why to sort large list of elements stored inside the hard disk will go for merge sort, and the beauty is that because it access the element in block. Okay, so next, meet in the next lecture.